Just do it.
Huh? Yeah, okay, so yeah, thanks everyone who stayed with us until the last day, yeah, and for everyone who didn't also, I guess. So yeah, we're very happy to have Yulan Qing today, and she's going to speak to us about boundaries of Croke-Kleiner spaces. So yeah, take it away, Yulan.
Thank you. Let me set up so I can see the time. I want to thank everyone. Now I cannot see who's here, but for coming on the last day. Today is going to be an easy day with just 3 one-hour talks, I think. Well, mine is 1 hour anyway. I don't know if it was advertised differently. But today we're going to talk about the boundary of one of the space that certainly fascinated me, but was at the center of a lot of these studies and why some of these works came about, which is the Croke-Kleiner spaces. And this was exhibited about 20 years ago, so quite a long time now, by Croke-Kleiner. You can think of this talk as an extension and complementary to Kim's talk. So if you attended that one, then all the definitions, and you're familiar with the definition and topology and all the basics. If you haven't, I'll define it somewhat quickly. Okay. So the visual boundary is defined for K0 space exactly like Gromov boundary, in the sense that I have a base point, although in the end it will be base point free. I'm looking at family of geodesic rays specifically, emanating from the base point. The equivalence class are by fellow traveling. Lastly, the topology is cone topology. Okay, so this is very straightforward extending of the Gromov setup. And just by doing this, we're able to get lots of good properties out of this. First, we have a space that is compact, and on which you can put a variety of metrics, and people do study it. I want to put the name Molly Moran, but that's only because that's the last paper that I came across. So I think it has a really rich topology, as you saw from the examples, but also that it has circles, it has supreme space carpet, zero dimension, a bunch of points, complex, nice subsets that's more like surface style. So compared to the ones that came after, it certainly has a rich amount of topology, can be connected or not connected, path connected, anything. And also it is already a good realization of the Poisson boundaries. If X is a K0 space with a co-compact action, then it was shown by Carlson Magoulas, and also Neville Sagiv, that the Poisson boundaries with reasonably suitable measures can be realized on the visual boundaries of the said K0 space. And lastly, there are some very deep results in the realm of Gromov hyperbolic space about how to connect the ends of space with the connectedness of the boundaries. So if the group is one-ended, then I don't forget which way it is, then the boundary is connected, I think. And this is much more hopeful to be extended on this visual boundary than on any of the ones that on Morse or sublinear Morse. Those frequently are totally disconnected. And there has been a number of work in that direction still. And the names are many. There's Mihalik, Ruin, Bensby, and many more, Haruska, so on and so forth. I don't know if this is even a partial list. So given all this good stuff, I wanted to say it is, at least at the time, it's very surprising that this topology is not naturally already QI invariant. And I want to point to the reason why. And from this example, even though it's been well studied now, I think if we were to move this theory forward to the next stage, this is still a very meaningful example to look at. So the plan for today is to cover this example. This is a maybe not exactly the first example, but certainly the first rank 1 example. Like just a Euclidean plane is already a good example of where boundaries can go around by a homeomorphism, by a quasi-isometry of the space. But that is a throwaway case for everyone. But this is a first case with enough complexity, in fact, to cover all rags. And later on, people extended to right-angle Coxeter groups, admissible groups, so on and so forth. So let's begin. What is the trick here? No, it's this one. I select this and make it big. Okay, so suppose I have 3 1 by 1 squares that I glued together, the upper and the lower edge and the left and right, to form tori. And these 3 tori each have their fundamental group, which I lined out. In fact, that's just the edge. The loops are labeled B, A for the T1, T2 has B, C, and T3 has C, D. And then I glue these torus together according to that particular labeling. So I have a tori complex that can no longer be easily drawn. And what I also have this object, the fundamental group of that tori complex, which is again generated by these 4 loops, A, B, C, D, where AB commutes, BC commutes, and CD commutes. I can decompose this group also as amalgamated product of the fundamental group of just gluing T1 and T2, in which case I get a F2 cross C, or just gluing T2 and T3, in which case I also get a F2 cross C. And these 2 identified over the middle plane. So this is the overall structure. But now if I lift this up, if I look at the universal cover of this object, of this tori complex, then I get what I will from now on be referring to as a Croke-Kleiner space, and also probably be using X to denote it. Should I write that somewhere? The lift of these. Anyways, okay, so what is the boundary of this object? As we saw on Monday, okay, if I start to look at T1 and T2, what I'm going to get is T2 will lift to a plane that, if I draw it correctly, will turn into a square. Oh, magical. And then T1 will just be, I'll be just drawn as planes coming out of it. And they're identified as the vertical B lines. So on and so forth. Okay. So there is more lifts of the red plane. That maybe I'll draw like over here. And then there's more lifts of the black plane. So if I look at the from top down, what I'm seeing is a tree factor, and if I look where we are right now, it's an R factor. So it's exactly a copy of tree cross R. Okay. So you can use the combination theorems that Kim talked about to realize that the boundary is going to be a suspension of Cantor sets. Or you can start to draw by hand that the first plane that we draw, the boundary of which corresponds to, suppose, okay, this I should draw it too fast. So if I draw it slowly and close it up, okay. So the boundary of the plane gives me a loop. The boundary of the black ones gives me more loops that, okay, so this should have the same upper point and lower point. And even this little red plane on the left side should still correspond to something that goes from the North Pole to the South Pole. In the space, it looks like somehow the top points, the top direction to be disjoint, but remember the equivalence class is by fellow traveling. And these directions, let me just be really clear that this are the same direction no matter where they occur, as long as they're pointing north. So these points are, I'll call them poles or pole points, and the rest of them are arcs. And this is a complete description of the boundary of this block. So let me write that down. That's a suspension of the Cantor set. I draw the lines as red and the black, but topologically we cannot distinguish. Topologically, we can distinguish just two types of points. One is a pole point, and one is a point in the middle of the arc. Because if you take a complement, you can see what you get is not topologically equivalent to each other. Okay, so similarly, if I take T2 union T3, well, not union T2, T3, and then the universal cover of that, I'll likely get, also should draw the red first. And then because of the specific orientation I'm chosen, the suspension is going horizontally. Okay, and some red ones too, so on and so forth. And like I said, the pole points here and the pole points here. So another suspension of Cantor set. So how do these two types of points come together? The two types of boundary come together? Well, what I can see is if for every red plane, it can actually be part of both. Is that clear to us? Yes. So if I have a red copy here, I'm going to start to see, I didn't draw this, this red plane over here can also be exactly one of the red ones of a block of the right kind. So I call these blocks the T1 and T2. That's one kind of block, and the universal cover T2, T3. That's another kind of block. Okay. So that is to see, whenever I see a red loop, it's going to be attached to both the first kind of block, the vertical kind, and the horizontal kind. So let me draw that somewhat clearly over here. Okay. So how many, so in some sense, I can see that those blocks are adjacent. Two blocks are adjacent if they share a flat. I mean, the universal cover, so there shouldn't be any, in terms of the structure of the blocks, that there shouldn't be any loops in here. That's a vague way of saying it. And every two blocks, if they share open subset at all, they should be sharing a plane. So that is to say, these blocks, even though they're entirely made out of flats, they organize themselves in a tree fashion. And that makes this space highly, highly hyperbolic, not by looking at it, but by tracing geodesics around it. And we'll see why that's useful. But let's get back to the substitution of Cantor sets. Suppose we call this first one, can I circle it? Suppose we start in this one, then every time I see a red loop, it tells me I can attach a horizontal one to it over here. And I see another another red loop, I can attach another horizontal one. In fact, I can attach uncountably many. And inside this horizontal one, inside each of this horizontal one, I'll be able to touch vertical ones, so on and so forth as well. So I'm out of water. Okay, so this tells us, this gives us kind of a complete picture of what's going on with these block boundaries. But that also tells me that I'm missing some of the points. So over here, in fact, there are more pole points, topologically speaking, than what's drawn. So every red loop, when you look at where the equator level, the level of latitude 0, you should also see a pole point. And if that's the case, then if I take the closure of all the pole points, the closure of all the pole points, then what I get essentially is the whole equator. So now I have more topologically distinguishable points. I have points on an arc that I have points, and then I have points that's right on the arc. I have points in the pole, but I also have points over here who is the limit point of pole points, as opposed to points over here who, if I look at its neighborhood, it's just it's not a limit point of pole points, and I have pole points itself. So I would say, in some sense, I have three types of topologically distinguishable things in the boundary. The reason I say that is because we wanted to start to change we wanted to have the group acting on two of these complexes that are slightly altered and see if there's a homeomorphism between the two. So now let's do that. Suppose I change the angle, the local angle between the B loop, C, and the, okay. So on which block should we do that? BC loop. Anyways, so that is to say, this angle is now changed. So maybe over here, if I'm still working with this, if I'm still vertical, okay, so I'm still working with this one, then this top I read is B infinity, the bottom is B minus infinity. This is C infinity, well, at least for that copy, this is somewhat traced by C minus infinity. If I copy that particular picture down here, okay, then the B infinity, B minus infinity, C infinity, okay, so C infinity should be a little bit more upward, right? C infinity, so, and C minus infinity. Okay, because now this angle is presumably 60 degrees. That's very good. And then still inside a bunch of red, black loops and a bunch of red loops. But now if I take the closure of the pole points, what I'm gonna see is, still I'm gonna see, even just on this block, I'm gonna see two isolated pole points, the B infinity and B minus infinity. But I claim here that I'm in fact gonna get the closure of C infinity is in fact going to be able to limit to all of the arcs. And similarly, the closure of the C minus infinity type of rays are going to get to be able to limiting to all types of arcs. So the reason for that is the words, the subset of words, or elements in F2 generated by AC, whose tail is C infinity, can be used to approximate and all other infinite geodesic rays in the boundary of F2. So just using C infinity, you can get to everything by just following any word for as long as you want, and then go to C infinity. You can even also use this to approximate C minus infinity, because you can first go C minus 5 and then move to A and then move to C infinity. But the same reason, but similarly, subset of words in F2 whose tail is C minus infinity, I didn't finish, has closure or complete to all of the boundary of F2. And similarly downstairs. So what used to be one equator now become two equators. That is to say, if I look at the black line, there'll be 2 points on the black line that become limit points of the boundary. So if I have a homeomorphism, so let G acts on x1, x2, where x1 is the Cartesian, the perpendicular, the BC loop is at 90 degrees, and x2, the BC loop is at 60 degrees, then what we see is those two type of boundaries, even just on the block, is already topologically different, because I can distinguish isolated pole points. No, this one over here. I can distinguish isolated pole points. Therefore, I can distinguish arcs going from pole points to pole points. And therefore, I can count either 1 or 2 number points that are a limit of other closure pole points. So this should hopefully by the time this is obvious, that there's no way these two boundaries are homeomorphic. And in fact, it was later exhibited by Julia Wilson that if you can play with the angle and come up with uncountably many pairwise non-homeomorphic boundaries. And this is a strong form of when we say this group may not have may not have a unique visual boundary, because the weaker form is just saying that the G-equivariant homeomorphism and a G-equivariant map is not a homeomorphism. In that case, you're kind of thinking about, instead of the K0 space, you're thinking about the corresponding Cayley graph, and therefore there's a clear way, there's a clear quasi-isometry to go from one space to the other. If that map mess up, that already tells you, even if those two places are abstract, or those two spaces are abstractly homeomorphic, that might not mean much from a group theoretic point of view. Okay, so very good. So now what do we do next? Don't have to, I can just write those myself. The next we're going to say, what if we fix the angle at 90? Fix the angle of intersection of BC loop at pi/2. Then is this boundary, and then do we have homeomorphic boundaries? So there's less things I can do to change the geometric action if I've asked the angle to be 90, but there's still some things you can do. You can change the translation length, for example. So the first case I've say is, yes, it's studied by Croke-Kleiner, but the second case is also in a later paper where they studied, the title of the paper is Geodesic Flows on Graph Manifolds. So it's also studied by him. But as opposed to just out of curiosity, you wanted to fix the angle, there are also a group that there actually exists, that there exists a group of reflections such that if these reflections act geometrically on this particular Croke-Kleiner space, then the angle has to be fixed at 90, such that if G acts geometrically, I think whenever I draw that particular arrow is always going to be geometric action, then the angles are fixed at pi/2. This is intuitively possible to accept, because on a plane, suppose to put a geometric action on a plane, one thing we can do is to, nice, it's always suspense if it actually turns into a square. Okay, let me change to a brighter color, is to look at two reflections that are parallel, so they don't have any relation, and another two pair of reflections that are also parallel, but they're each commute with the first two relations. So I'll label these A1, A2, and the other two B1, B2. This way I have a nice action that is by isometry, properly discontinuous, and co-compact. So the correct group to act on this is called right angle Coxeter group, which a lot of you know a lot about. And the presentation is also not difficult. Instead of writing out the presentation, I'm going to draw the diagram that's even simpler, I think. So A1, A2 commutes with B1, B2. B1, B2 commutes with C1, C2, and C1, C2 commutes with D1, D2. Again, that's one particular example of right angle Coxeter groups, but at the time, it was just as unknown if these groups in particular would be much better candidate to have unique visual boundaries. Okay, so let's study these. Now, the first thing we're going to do is consider the tree of blocks. just to remind you, the blocks are just either covers of T1 union T2 or covers of T2 union T3. And the tree, if we believe ourselves, would look something like this. It will be locally infinite because each block of one type, horizontal block, would be adjacent to, where adjacent means adjacency. So suppose each vertex represents a block, then the adjacency would mean sharing a particular flat, sharing a flat, okay? And each horizontal block is adjacent to countably many, yes, countably many, but infinite vertical blocks, and each vertical block is also adjacent to countably many, but infinite horizontal blocks. So the tree looks like this, goes on and on and on. This object will look very much similar to all the several other objects that you have heard about throughout the week, such as, maybe not similar to, but quasi-symmetric to, maybe curve graph or something. But it is also the Basser tree associated with the amalgamated decomposition. If you want to understand it algebraically, but we don't. Well, we don't. We're not going to. What we're going to do instead is consider. Suppose I have a geodesic ray, starting at the base point x0 and goes to infinity. I claim that it has a very clear, well-defined itinerary through the blocks. So for the first finite amount of time, could be infinite, it will be in one block, and then it will exit that one and never be able to return because we're in a Cat0 space, but also because these are convex objects. So it will go into B2, B3, B4, and maybe B5, and just end up staying the rest of the time in B5. When I say go into the block, I really mean you have to not just stay on the plane where you go from where on the plane where they share, but you have to leave that common plane and go inside the block. So that is to say there's a shadow, maybe erase this or else I cannot shadow correctly, from the geodesic ray up into the tree of blocks or the Basser tree. That gives you a path, in fact, a geodesic path. If this path is finite, then we end up on the conglomerate of suspension of Cantor set that we were looking at. But if this a path is infinite, which a priori could be, then we haven't talked about yet. So now let's talk about what if the projection was infinite. So if the projection was infinite, there something to do. I drew over here of an infinite itinerary geodesic, and some of the parts of the geodesic, what it should look like or where it should reside. My claim is that suppose I know which path, so the input data is just a path in the Basser tree, which turned out to be not BS at all. Okay, so that's the only thing I know. Then I would say based on that path, I would know exactly which plane that of the middle, which lift of the middle torus that I should leave in order to enter the correct block, because each two only has one particular plane in common, so there's no choice. So this plane, the entry plane, which is always red represents the middle torus, and the exit plane are uniquely determined. Exit, not exist, are uniquely determined. But if this is the case, then I will say everything that happens in the middle is also uniquely determined. This is firstly true from the tree direction. If I look at the tree direction, should I further explain that? I think so, might as well. And this is more unique to trees, but if I look at the tree direction, I guess the orientation I'm choosing is such that I choose these, mark these as red and the horizontal ones as black. But if I know that I enter here and leave here, then there's only one particular way to go in the middle. Okay. So when I draw it as a complete flat object like this, it just means that it's a geometric flat. It does not correspond to any particular lift of any torus, but it is there uniquely. So if I know what's happening before and after, I certainly know what should happen in the middle. But since I have an infinite itinerary, then I know my unique, just based on the input data, I also know my entry point before that entry point. So the next, and I know my exit plane after my exit plane. So I know all these red ones very well. And that means I know all the in-between ones too. But the local geometry of this object is such that if I were to follow this template, well, I guess I should back up and see what I'm trying to do. I'm trying to do is based on this input data, which I now highlight, I wanted to know what is the boundary object corresponds to this particular entry data, this path. Is it a point or a circle or an interval or a Pinsky's caput? This is the part I'm interested in. The part that stays in the tree, I already figured out. Okay, so continue. If I'm over here, I wanted to go somewhere from over here to over here, then even though I can arrive anywhere onto the red plane, and from the red plane, I can transition anywhere onto this vertical plane, and on this vertical plane, again, I can go however I want, and then arrive on the green plane again and keep going. So this is the case. But just by virtue of the fact that I'm dealing with a particular geodesic makes me realize I should stay in this corridor. Okay, so this is something you know if you go into a very complex compound of buildings, and all of them are related, and you want to go from one part to the other. And there's certainly lots of these things in Shanghai. So in order to go very quickly from the first building B1 to the third building B3, even though you wouldn't want to go above the floor where you came off, and you don't have to go lower than the floor where you're going to exit. So this is as simple as that. So knowing just adjacent group set of 3 or 4 blocks, I'm able to create this particular template. So since my data is infinite, I have an infinite number of template of various shapes to put together. What's also worth noting is that these templates, so if I draw another one, they don't come at a, okay, let me draw them in straight line as well. Suppose the next one is like this. They don't meet up exactly. They meet up in these kind of quarter planes. Okay. But the way they meet up is such that, so maybe I should draw more clearly as, so for the middle one, I know I have to enter somewhere over here. So, and then I know I have to exit and then enter somewhere into this, so on and so forth. So it's less lined up, well lined up than you think, and something like this. Okay, but you can still take them and kind of unfold them to such that to put them together to realize that if we spice all the possible areas where such a geodesic could travel together, they look like part of an imaginary Euclidean plane or Euclidean sector. And this is to say that there's there's not going to be a Sierpinski's carpet are associated to this particular input data. It's just going to be geodesics that reside on this particular connection of templates or this particular sector. So therefore, now we can apply what do we know about the size of these templates. So one thing off the bat, what we can say is that if a geodesic travels through templates of all bounded size, then so the template itself looks like a bounded neighborhood, then it okay, so maybe I don't want to say that. If the templates are of all of bounded size, then there's a unique geodesic at the infinity. Geodesic ray at infinity associated with this template. So I can go back and immediately start to exhibit a bunch of templates with this property. These templates are nothing. We said our input data is just the group. So these templates themselves will look something like, I have something suspicious written there. I wouldn't write that, but the gray ones, their side should be just words in AC. And then the other side should be words in B, some number of words in B. And then the quarter ones are words in BC. And then you enter the new block where the sides are now words in in BD. Now you're in the BD tree. You have an embedded plane in the BD tree, and the other side is all C. So these are the things you can read off the group information. Okay, so these are Morse, in fact. Okay. But if these planes, these panels, the boardwalk is not exactly bounded size, then a priori one could imagine that if they grow fast enough, then I would have two geodesics traveling through both of them, and these two geodesics are not fellow traveling either. So they could potentially correspond to a whole arc and uncountably many points at infinity. Okay. So maybe I didn't leave myself enough space, so let me get rid of that. So what I'm trying to say here is that, back to black, I would have a union of the block boundaries, which I now simplified to something that looks like this. We can also refer to as a core, which is the union of the boundary of the blocks. That's some item. And then aside from that, I should have a whole lot of points. These points are not isolated. We'll talk about it in a minute, although they will be isolated if you take the Tietz metric, and something we talked about on Monday. But they should also be a bunch of intervals. And if you chase down this construction or this explanation closely, they're close intervals. And each one, and all of this should be an uncountable set. I think this should somewhat be a complete description of the blocks, of the boundary, because a geodesic, when you shadow to a Bassier tree, is either finite or infinite. The finite ones look like these, and the infinite ones look like these. Okay. So what's the story here? The story here is that we just exhibited, we said if the templates are all bounded size, then it's going to be Morse. But it's conceivable. Okay, so how could I get space? Just keep erasing. It's conceivable that to have a template such that when you change the size of the fundamental domain, the length and the width of the fundamental domain without changing the angle, then the asymptotic shape, by which I mean whether it accommodates one ray or really a whole segment of rays, as a whole sector of rays could change, then the boundary changes. You have a lot to work from. So you start to come up with this. So you start to look for examples. And the examples I wrote very tiny over there, I'm going to copy down again, is that in the first block, I will have a b square. And then in the second block, I will have, can't remember, c squared d. So I drew the wrong thing. CCD. And the third block, I'm talking about part that's strictly inside, not the ones, the red planes. I'll have double those. So a B, 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 B. And the next one is also double of those. Anyways, so on and so forth. So I have a panel that's in some sense self-similar. That is not important, but it's grown exponentially. If I have something like this, then that is a specific example where I then change. So if I keep them all square, in the end, I get some kind of object. But now if I change the length of A to double, or go back to the language of right angle Coxeter group, I can simply increase the distance between the two reflection axes and also change the C, the distance between D1 and D2 to double. If this is the case, then I'm confronted with a different type of panel, different type of template, such that all of a sudden, now I'm confused. Maybe in the second case, I get a point. In the first case, I get an interval. But in any case, I can go from a point to an interval by applying this particular quasi-isometry. And this, again, this doesn't mean that these two spaces are not abstractly homeomorphic. It's just that, let me draw this over here. I suspect that's not all of it, because there's a subset of the points and the subset of the intervals that are not QI invariant, that you can go between them. Okay, so this is also another reason, aside from the first argument, this boundary is not QI invariant. Now, what is a sublinearly Morse boundary of this space? As you've heard from the results of Durham and Abdul, and also results presented by Kasper, that we can simply look at the excursion. Well, I don't know, I think Abdul have other different methods or different arguments to put it in the curve graph, but in this, I guess it's the same. We can look at the excursion of geodesic rays, and if the excursion of the geodesic rays through these templates are bounded above by a kappa function, then it is conceivable that this geodesic ray is kappa linear. Another way to argue that is also, again, let's look at this geodesic ray, and let's look at that goes through B1, B2, B3, B4, so on and so forth. And this ball itself is somewhat disjoint from the geodesic ray. Maybe it's centered in B3, and it certainly has lots and lots of other, probably go through many other blocks, maybe also go through block 2 and 4. But the projection of this ball to the geodesic ray should lie uniformly in a finite number of adjacent blocks. And the reason for that is, again, something you can understand by these blocks space split and connecting to each other in a tree-like fashion, such that if let's say block 5, if block 5 is also here, then the geodesic from B3 points in B3 to B5 would have to be forced to go through B4 as opposed to be up here, because B5 would have mutually huge projection to each other. And this is coined many times in different phenomena, but I think the fact that they are spliced together in a tree-like fashion means they have, among other things, bounded. So the idea was bounded geodesic image theorem. But we also saw this as one of the reasons, one of the features of hyperbolicity is the projections are bounded, and just by the fact that pathways are narrow. So let me write that down if that was not clear. Balls that are disjoint from geodesic ray, which we'll now call beta, projects to a uniformly bounded number of blocks. Let's say 5 blocks. Whether it's 5 or 50 doesn't matter. Therefore, if the projection, if the excursions are kappa bounded, then the projections are kappa bounded. And since we're in a K0 space, that means they're kappa Morse. So should we still go back to this? That means there's a small set of points here that are sublinearly Morse. And instead of that, if you decrease kappa, you have subspace and subspace of sublinearly Morse boundaries. And further inside that, when you let kappa equals to 1, you get the Morse boundary. I don't know how it was the original Morse boundary connects to this topologically, but with the Cauchy-Mackay topology, so the Morse boundary under Cauchy-Mackay topology which is the paper we should all read, is a subspace. In fact, it's a subspace topology in the sublinear boundary. Okay, so there's more points in there. And then what happens over here on the other side? I don't know. So what else? I should also say that, which I already erased, that we know from Durham and Zalum that this boundary is a continuous, there's a continuous injection from the boundary to the boundary of the Bat-Seer tree. But we can just prove with this particular example, and it turns out the argument extends to almost all of these things, almost all writing and arting groups, where instead of blocks, you look at maximum joints, and instead of these red planes, you will take strongly separated hyperplanes. But the spirit of the argument is the same, such that it's a continuous injection into the boundary of the Bat-Seer tree, which is totally disconnected on that. But just by looking, just by defining the open sets in the sublinear boundary itself, we can show that the kappa boundary of X is not compact. I think that's obvious. Totally disconnected. And has no isolated points. It has no isolated points in particular because you can approach it with Morse geodesics. So you can have, I suppose you can also approach it with geodesics that lies in a flat. So let's go back here. Suppose now I have geodesic ray that follows some of this template. I should go this one. Follow some of these templates, but not all of it, and then just spend the rest of this time in some block. And then the next one follows longer, but spends the next time in the next block, so on and so forth, or even in the red ones. I can use, in visual topology, I can use this set of rays to approximate the rays at infinity. And that is to say that in the visual topology, I can think of tracing along the arcs that goes from poles to poles until at the limiting behavior of this point of this activity is sometimes a point. This corresponds to those points. And sometimes this limiting behavior is a segment, very much like the topologist sine wave, where you have, it's just inches onto the segment. In the sublinear Morse topology, it's a similar phenomenon because we can argue that the kind of geodesic rays that pass through a same set of templates, maybe same set of these panels, maybe not one of them, but several of them, these can give us open sets. And via these open sets, we can tell that there's the Morse, you can have Morse geodesics that follow through the first three panels and then just repeat this pattern to infinity, and then a different Morse geodesics that follow through the longer pattern and then start to repeat. So the Morse geodesics themselves can also be limiting onto the otherwise sublinearly Morse. So this is one of the many arguments that are never isolated. So is that everything I want to say? So now what do we do with this example? This one. Move it over here and make it larger. Okay. Move it over here and make it larger again. Okay, this is not as easy as just writing things by yourself. Okay. So there are many interesting things happening with this example. You can look at this phenomenon, like I said, and instead of using these simple structures, you can consider extending the argument to all rags. And it turns out you can do that. So using this similar argument that I just described, you can trace, you can track down all the sublinear boundaries of rags and prove that certain geometric features such as excursion would give you the Morse property, the sublinear Morse property. You can also extend it to what's called K0 admissible groups. I should read, this is also first studied by Croke-Kleiner in great detail, but most recently by Yang and Hong, using the more modern tools such as projection complex and so on and so forth. So what are they talking about? They're still talking about K0 groups gluing along. So quickly, this is K0 groups, GI, gluing along flats Z2. But each one of these is such that the center of GI is Z, and GI mod its center is hyperbolic. Okay, so it's just based on the tree cross R, you can come up with, so instead of tree, you get hyperbolic. Instead of being a group product, it being a metric product. And you can run through the similar type of arguments and deal with more things. I also wanted to say this is a group, the example in which there's that's not so related, there's a continuous divergence spectrum, which means there exists for any superlinear function. We know that from works of Baerstock and Charney, and possibly works that before that, that the divergence of these in this group is superlinear, but there is, for every superlinear function, you can find a pair of geodesic rays diverging at that rate. So the divergence function is, there's no dichotomy such as a linear or exponential or linear or polynomial of degree 2, so on and so forth. There's just continuous spectrum. Okay. So since I have loads of time left, I'm going to talk about open questions. The first is, I left a gap, not very visibly, between these. So I said the dust, the stuff that's outside of the core, is made up of a bunch of points in a bunch of intervals. Some of these points are not QI invariant. By just one particular example, if you allow yourself the flexibility of angles, or if you allow your flexibility of angles, then this object is also not QI invariant. But I imagine you'll be able to include more points and more intervals to be the ones that are not reliable. But we also know from this whole week that there's a subset of points that are completely reliable, which is sublinearly Morse, and inside which is Morse. But I left 3 dots, in fact, uncountable many on the outside, but I don't know for sure. So my open question is, are there points that are neither? Did I write that nicely? Are there isolated points in the T's boundary that are not in the kappa boundary and is QI invariant? If the answer is no, that means there is some kind of maximality claim to this approach. I don't know how to put that in a reasonable sentence, that somehow this particular viewpoint, at least on this one example, is you're able to collect all QI rigid ones. But I suspect the answer should be yes, there should be a bunch of them, one possible candidate would be things that possibly diverge a whole lot. I use this, the templates are huge, but then in between the huge ones, there's small ones that creates a bottlenecks. So in terms of quasi-geodesics straying away from geodesics, they're not sublinear, but somehow these bottlenecks also don't allow us to introduce to geodesics that diverge away. I don't know if those actually exist. I think so. But if that's the case, that tells us there are ways to build equivalence class that are QI invariant that we have not explored. So there's a further step to enlarge the current definition, the current viewpoint, to include points at least suitable to this particular example that we don't know about. We should look beyond those.
Yeah, can I say something about this?
Yes.
I think I talked about this with Jason Burstock at some point and Mark Hagan. I think like in the ABD construction, in the particular case of RAGs, in the ABD construction, the top level curve graph is the contact graph, and that's stable under quasi-isometry. So if you have like a right angle arcing group quasi-isometric to something, then the contact graph of the two is going to be the same, and it's going to be the same up to quasi-isometry, and that's strictly larger than the kappa boundary. So I think, yeah, there are more things but that's just
so those two hyperbolic graphs are QI invariant because those are hyperbolic graphs that are of the same topological type. But when you blow it up and look at it on the map, then I understand your point. There's strong evidence to suggest there should be a larger QI invariant set even on the graph by projecting it onto the curve graph. That's the point.
Yeah,
right?
I'm just saying like the top level curve graph that even in HHS in general, the top level curve graph that results by the Abbott, Burstock, and Durham's construction, it is invariant under quasi-isometry. So if you change the HHS by quasi-isometry, the top level curve graph remains the same, and that is strictly larger than the image of the kappa boundary, right? Because you can stay in a flat as long as you want.
Well, my answer to that is the top level curve graphs they're all of the same, not all of the same, they're mostly the same, they're the same topological, the boundary of that is the same topological space, because those are all locally infinite and infinite diameter curve graphs. I don't know what I'm saying. I'm saying that that gives you itinerary, but not give you the local shape of these directions. That is a different object on which this R object project upon or something, right? For the same reason here, if you look at the top level curve graph, you wouldn't be able to detect the lack of QI invariance between the points and the interval.
So yeah, I see what you're saying. Okay. Yeah,
that's a different, very robust QI invariant object that's associated with the group, but not QI to the group. Right. But I don't know the ABD construction at all. So maybe I misunderstood the objects that we're talking about.
Well, actually, can I also like maybe interject to this? I'm just trying to understand what you're saying. So I mean, first of all, I'm not sure what you mean by they're quasi-isometric. Like, how can you say a type of points are QI invariant? Like, what do you exactly mean?
What I mean is if you have two HHSs, then...
No, I'm asking Yulan. She said
sorry, my bad.
No, I understand the curve complex thing, yeah. Like, what
so any quasi-isometry, that apply to this particular space, these points belongs to an invariant set of points.
It has a set. So you want a geometric property. Yeah, you want a geometric property that is also invariant. Yeah. So, okay, so combine the two things you're saying. Like, I think if you want something close to like recurrent or something. So there's Morse, which means you stay in a thick part all the time. There's sublinear Morse, which means you spend a lot of time in a thick part or something. And then there's recurrent, which means you infinitely often you come back to the thick part and spend a lot of time, right? So these are the guys which go to infinity in the curve graph, right? In your thing, which means like there is like, it's not this, yeah, there is Morse pieces appearing in them like infinity often. Right. So yeah, I mean, but you have to make it into topological objects in general. Yeah, but
right, exactly. So it indicates that there are ways to extend the definition to include more a bigger topologically invariant subset.
Yeah, that's right.
Yeah. I don't know what's happening with the points underneath, so I'm not gonna say more about that. Also, it seems to me that if we were to compactify this space, it's highly unlikely we'll get something still as nice as metrizable, because this huge object over here itself is already wobbly. So we have to somehow, without coming up with a new viewpoint, we have to get rid of this component altogether, which people have done, like both Morse, the construction of Morse boundary and sublinear Morse boundary have gotten rid of that object for that reason. Okay. So specifically, what are the others? So the second one is, are all the kappa boundaries homeomorphic? I don't know if this is answered in full generality, in partial generality, or so on and so forth. Without co-compact action, you can certainly come up with examples where as the kappa gets smaller, you start to lose points and they end up not being homeomorphic anymore. But with co-compact action, maybe there's something to be said. And I think this next question might already have an answer. Are all the kappa boundaries disconnected? There are not, certainly if the space is Gromov hyperbolic. But when I look back at my notes, it suggested that there are examples residing in right angle cluster group where the space itself is not strictly Gromov hyperbolic and the boundary is not disconnected due to Baerstock. But I didn't have time to check it in. And the last is, what is the higher dimensional phenomenon of kappa Morse? This is the question that I guess I'd add at the end. And there I end my talk. Thank you very much.
Thank you. Yeah, thanks a lot.